Okay, now we're up and rolling. So, in general, perhaps, okay, the hydrocarbon chains are generally 15 to 25 carbon atoms long. So now we've got that backbone, beautiful esters, and we've got those nice long chains. Generally, we're going to have an even number of carbons overall, because a lot of the time they are formed from 2 carbon units. And if I have a container of a lipid, like butter, if I have a thing of butter, there's going to be a mixture of chain lengths and degrees of saturation within that, and I just classify it based upon the most predominant one that there is. So we know butter is a solid at room temperature, bless you, so it's going to be mostly unsaturated, but there might be some saturated lipids mixed in there. We're going to have some different ones with different chain lengths, but overall I've got my lipid that is butter, that is unsaturated. Since it is a big range of degrees of saturation and chain lengths within any given thing, I'm going to see a range of the melting points. So it's not like with water. I have, at this temperature, water is going to melt. It's going to go from a solid to a liquid. Our oils, fats, our lipids, they're all going to change from solid to liquid at a range of temperatures because of these differing chain lengths and degrees of saturation. And in general, if we have a saturated lipid, we're going to have the general formula of CnH2n plus 1 COOH. That's my general formula for a saturated hydrocarbon. So you might see questions asking how many double bonds there are in a specific lipid, and you can figure that out because you can figure out how it differs from this general one where there's no double bonds. Okay, let's make sure we're all awake this bright and shiny morning. That's not at all bright and shiny. True or false? A, true, B, false. Saturated fatty acids are mostly fish and plant-based. Saturated fatty acids are mostly fish or plant-based. Is that true, A, or false, B? And this one, and let's see. Most of you are saying false. I agree completely. That is because saturated means that there's no double bonds, which means we are going to be mostly animal-based. Good job. Okay, fats versus oils. The melting point and the hardness depend upon a couple of things, one of them being the average length of hydrocarbon chains. Bless you. The degree of unsaturation, so how many double bonds there are, and whether the hydrocarbon chain is cis or trans around the double bond, and we're going to see what those are in just a little bit. So the average length of the hydrocarbon chain, the longer the carbon chains that we have, the greater the molar mass, which means there's more places for those intermolecular van der Waals forces. We're dealing with lipids, so they don't have nice hydrogen bonding or dipole-dipole bonding. Our predominant force is van der Waals. So the bigger we are, the higher the melting point. Takes more energy to get those big things to part and go from a solid to a liquid. The degree of unsaturation, which is also going to have an effect on melting point and hardness, we know that double bonds make chains less straight. Since they are less straight, there's going to be less van der Waals forces, which means they're going to have a lower melting point, which makes sense because the ones that are unsaturated or polyunsaturated, that has multiple or single double bonds, they're liquid at room temperature already. Thank you. They've got that lower melting point. Okay. Whether the hydrocarbon chain is cis or trans around the double bond, what this is generally called is geometric isomers or isomerism or isomerization. So geometric isomerism. Geometric isomerism. So you've got the same thing, but because of the double bond, they're not going to rotate as easily around each other as single bonds do. Single bonds we can move all around, but that double bond kind of holds it in place, and it holds it in place either in the same direction or in opposite directions. So the cis going in the same direction, trans in opposite directions. And again, we're looking at the double bond. Looking at what's happening with the double bond. The cis have a lower melting point than similar trans, so if we have the same sizes of the stuff, if that's comparable, if everything else is comparable, we just have a cis versus a trans, then the cis has the lower melting point, and that's because they can't arrange side by side well. So this is decreased van der Waals forces. Cis is most common in unsaturated fats and processed unsaturated fats. Like margarine. Move this around. The processed fats go with the trans. That's my margarine. The trans is worse for your body because it's going to build up better. Builds up in a worse manner because it goes together better. Mm-hmm.
So how do they take, like, how do they make like hydrogenated oils?
We are going to get to that very soon. Good call. Okay. Unsaturated oils are less stable than saturated oils because they have those double bonds. We know double bonds are more reactive. So they are less stable for less time. The biggest concern is autooxidation. Oxygen around it reacting and breaking those double bonds. And at this point it becomes rancid. We get odors and flavors that we're not expecting. So we know these double bonds can break on their own with the oxygen around them, autooxidation. If they're in UV light, we can also have photooxidation. So the light UV rays act to catalyze the reaction. And we're also prone to hydrogenation and hydrolysis, as well as enzyme catalyzed degradation. Is there one in the back empty? Because I will get more if it is. It's behind the cups and stuff back there. That's okay. I was just wondering if I need to replace it. Okay, hydrogenation is reacting with H2 to break that double bond. Okay, it is empty. Good to know. Thank you. Okay, hydrolysis is this reaction with oxygen, so both of these count as hydrolysis, and they react to form water. And fatty acids that are free. That's where we get those icky smells and tastes. And this hydrolysis is the reverse of esterification. Where we take a carboxylic acid, bless you, and an alcohol and react them like we did with the wintergreen lab. Enzyme catalyzed degradation, most often we use lipase for that. It's the enzyme that catalyzes the reaction. And we know that they're less stable than saturated, which also means that the more unsaturated we become, so the more double bonds we have, the more reactive it is. Because there are more places to react. Yep.
Does that mean that unsaturated oils burn better than saturated ones? They're more reactive?
I don't know if they necessarily burn easier. That's a good question. I don't know. Okay, they're therefore likely to become rancid faster. So they have a shorter shelf life. So So hydrogenation, which is what Noah was asking about, that's reacting hydrogen with that double bond, breaking that double bond. If we take a look here, so I have a carbon-carbon double bond and a bunch of other stuff there as well. The hydrogen with some catalyst, maybe we need some nickel in there as well. Maybe we just have some UV. They're really reactive, so we don't need a whole lot. Breaks that double bond. One hydrogen is added to each of the carbons. There's some advantages to doing hydrogenation. We can go from a semi-solid to a solid state. We could go from liquid to semi-solid, liquid even to solid. It's more stable. The texture is controllable. But we're messing with chemistry, so there's disadvantages as well. And that's that they are unhealthy in comparison to this unsaturated fats or lipids. All those oils are healthier for us because they're not going to build up as nicely in the transformation in our bodies. Duncan?
Are we doing anything for mold in this class?
We are going to vote on the moles for the other kids. 1023.
Can we make moles?
You could. Yeah, you're not going to get anything for it, so